This session, we will study about colligative properties. They are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Colligative properties are properties of the solution that depend only on the total number of solute particles in the solution and are independent of the chemical identity of the solute particles. The colligative properties are relative lowering of vapor pressure of the solvent, depression of its freezing point, elevation of the boiling point, and osmotic pressure of the solution. These properties helps in the determination of molecular masses of the solute dissolved in the solvent. First, we will discuss about relative lowering of vapor pressure of the solvent. According to this property, when a non-volatile solute is dissolved in a solvent, the vapor pressure of the solution formed is decreased compared to the vapor pressure of the pure solvent. Based on this property, the equation to find the molecular mass of the solute is given by P1 minus P1 divided by P1 equal to W2 into M1 divided by M2 into W1, where P1 is the vapor pressure of the pure solvent, P1 is the vapor pressure of the solution, W2 is the weight of the solute, M2 is the molecular mass of solute, W1 is the weight of solvent, and M1 is the molecular mass of solvent. Let's deal with an example. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram when added to 39 gram of benzene whose molar mass is 78 gram mole inverse. The vapor pressure of solution is then 0.845 bar. What is the molar mass of the solid substance? From the question, it is clear that the vapor pressure of the pure solvent, that is benzene, is 0.850 bar. The vapor pressure of the solution after adding the solute is 0.845 bar. The molecular mass of the solvent, that is benzene, is 78 gram mole inverse. The weight of the solute is 0.5 gram, whereas the weight of the solvent is 39 gram. Substituting all values in the equation, we will get the molar mass of solute is 170 gram mole inverse. The next colligative property is elevation in boiling point. According to this property, when a non-volatile solute is added to the pure solvent, the boiling point of the solution is elevated or increased. Here we can see that when the solute is added to the pure solvent, there is a difference in temperature between the normal boiling point and elevated boiling point. According to this property, the equation to find the molar mass of solute M2 is given by 1000 into W2 into Kb, the whole divided by delta Tb into W1. Where M2 is the molecular mass of the solute, W2 is the weight of the solute, W1 is the weight of the solvent, delta Tb is the change in the boiling point, and Kb is the boiling point elevation constant. An example, the boiling point of pure benzene is 353.23 Kelvin when 1.80 gram of a non-volatile solute was dissolved in 90 gram of benzene. The boiling point is raised to 354.11 Kelvin. Calculate the molecular mass of solute. The boiling point elevation constant or Kb for benzene is 2.53. Here, the value of delta Tb or change in boiling point is 0.88 Kelvin. The weight of the solute is 1.8 gram, whereas the weight of the solvent is 90 gram. Substituting all values in the equation, we will get the molecular mass of solute or M2 is 58 gram mole inverse. The next colligative property is depression in freezing point. According to this property, when a non-volatile solute is added to the pure solvent, the freezing point is depressed or decreased. Here we can see that when the solute is added to the pure solvent, there is a temperature change between the normal freezing point and the depressed freezing point. The equation to find the molar mass of solute is given by Kf into W2 into 1000, the whole divided by delta Tf into W1. Where M2 is the molecular mass of the solute, W2 is the weight of the solute, W1 is the weight of the solvent, delta Tf is the change in the freezing point, and Kf is the freezing point depression constant. An example, 1 gram of a non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.40 Kelvin. The freezing point depression constant of benzene is 5.12. Find the molar mass of the solute. It is directly given that the change in freezing point is 0.40 Kelvin. 1 gram is the weight of the solute, whereas 50 gram is the weight of the solvent. The Kf value is 5.12. Substitute the values in the equation, we will get the answer 256 gram mole inverse. Now we will discuss some applications of depression in freezing point. In cold nations like Canada, where the temperature is below 0 degrees Celsius, there is a possibility that the water or coolant used in the radiators will freeze. To prevent this, a solute called ethylene glycol is added, which depresses the freezing point of the coolant. An appropriate amount of solute, ethylene glycol, also called antifreeze, is added, which depresses the freezing point of the coolant. Another application of depression in freezing point is the removal of ice or snow from the road by the addition of sodium chloride. In this method, sodium chloride or calcium chloride is added to the snow, which depresses the freezing point of water, and the water melts away easily. The solute depresses the freezing point of water to such an extent that it cannot freeze. The next colligative property is osmotic pressure. Before dealing with that, we should have a clear understanding about osmosis. The small solvent molecules such as water can very easily pass through the holes of the membrane, whereas the bigger solute molecules are unable to pass through them. Such membranes which are selectively permeable to certain molecules are called semi-permeable membrane or SPM. These membranes can be of natural origin or synthetic origin. Osmosis can be defined as the movement of the solvent molecules through the semi-permeable membrane from the lower concentration solution to higher concentration solution. The process of osmosis ends when the concentration of solute becomes equal on either side of the membrane and equilibrium is attained. The flow of solvent molecules from the lower concentration to higher concentration can be stopped by applying an extra pressure on the higher concentration side. The minimum pressure that should be applied on the higher concentration side to prevent the flow of solvent molecules is called the osmotic pressure of the solution. Thus, the osmotic pressure pi of a solution can be defined as the excess pressure that should be applied on a solution to prevent osmosis from taking place. The osmotic pressure, similar to other colligative properties, depends on the concentration of the solute. The equation to find molar mass of the solute is given by W2 into R into T, the whole divided by pi V, where M2 is the molar mass of the solute, W2 is the weight of the solute, R is the gas constant whose value is 0.083, T is the temperature, and V is the volume. An example, 200 cm cube of an aqueous solution of protein contains 1.26 gram of protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 raised to minus 3 bar. Calculate the molar mass of the protein. The osmotic pressure is given, that is 2.57 into 10 raised to minus 3 bar. The volume should be converted to liter, that is 0.2 liter. Temperature is 300 Kelvin. The value of R is 0.083. Substituting all values in the equation, we will get the answer as 61.022 gram mole inverse. Next, we will study about isotonic solutions. These are solutions having the same osmotic pressure. For such solutions having the same osmotic pressure, no osmosis occurs on the either side of the semi-permeable membrane. This is the reason for which the intravenous injections are having a concentration of 0.9% mass by volume, which is isotonic with the blood. Due to the fact that the injected solution as well as blood are isotonic, that is, they have the same osmotic pressure, the solution easily passes through the red blood cells. A pure sodium chloride solution with a concentration more than 0.9% is said to be hypertonic solution. It is having an osmotic pressure more than that of blood, and the red blood cells will shrink when placed in such a solution. On the other hand, pure sodium chloride solution with a concentration less than 0.9% is said to be hypotonic solution. These solutions have an osmotic pressure less than that of blood. The red blood cells will swell or even burst when placed in such a solution. It is important to note that a high intake of salt in the food can lead to a higher concentration of fluids in the body tissues due to osmosis. This will result in the swelling of the body parts, which is called edema. Next, we will discuss about reverse osmosis. This process is used for the desalination of seawater. In this process, a pressure higher than the osmotic pressure is applied on the saltwater side. During this process, the pure water from the salt water moves through the semi-permeable membrane to the fresh water. This process is called reverse osmosis. This process is often used for the desalination of seawater.